In Deadlocks Part 1, we have seen what is a deadlock, then we have moved on to a resource allocation graph, then wait for graph, right? So in Part 2, we are going to focus on the necessary conditions for a deadlock to happen. So let's dive in. There are four necessary conditions for a deadlock to happen. One is mutual exclusion, hold and wait, no preemption, and circular wait, right? So if there is a deadlock, then all these four conditions should be present. But the converse is not true. If all these four conditions are present, we cannot say it is a deadlock, right? So the necessary condition means if there is a deadlock, then there will be a mutual exclusion, hold and wait, no preemption, and circular wait. Right? So let's see what is a mutual exclusion first. Let's say there is a shared resource. This shared resource can be a CPU, memory, printer, or any software or hardware device. Multiple processes can try to access this shared resource. Let's name the process as PI, PJ, PK, and so on. There can be many processes like this which can try to access the shared resource. When multiple processes try to access this shared resource, there can be a synchronization problem. To avoid the synchronization problem, we have many mechanisms, and one mechanism is to guarantee mutual exclusion. So mutual exclusion allows only one process to be in the critical section. This shared memory will be a critical section. Okay, so if more than one process try to access the critical section, what mutual exclusion guarantees is that at a point of time, only one process can be inside this critical section. Other process will wait outside the critical section. Once this process gets done its job inside the critical section, it will move out and will allow the other process to enter into the critical section. Right? So this is only mutual exclusion. If there is a deadlock, then mutual exclusion will surely be present. Fine. So what is the second condition now? Here is an example for hold and wait. So there is a process PI and process PJ, right? So PI is holding resource A and waiting for resource B. This is known as hold and wait. So process I is holding resource A and waiting for resource B. Process PJ is holding resource B, right, to complete its task. After it completes its task, it releases the resource RB. Then PI, which is waiting for RB, can take up this resource. So both these are single instance resource. So this is the concept of hold and wait. The third one is no preemption, means, for example, a process, let's say PI, is executing certain line of code. When a new process PJ wants to access the CPU or any resource, this process PJ will get preempted and that resource will be assigned to the new process PJ, right? This is the process of preemption. But in deadlock, no preemption is allowed. Okay. Then the fourth one is circular wait. So this is a resource allocation graph, right? We have seen it in part 1 video, how a resource allocation graph looks like. Here process PJ is holding resource RB, right? And process PI is holding resource RJ. Similarly, process PL is holding resource RD and process PK is holding resource RC, right? And let's check what a circular wait is now. So PJ is waiting for PK to release resource RC, right? See this arrow, this one, this arrow, right? So process PJ is waiting for RC, right, which is held by process Pk. So process Pj is waiting for process Pk. So what graph is this I am drawing now? It is a wait graph, right? Let's see now process Pk. Process Pk is holding resource C and requesting for resource D, which is held by process L, right? So process K is waiting for process L to release the resource RD. Similarly, process L is requesting RB, right, which is held by process J, right? So see here, it forms a cycle, right? This wait graph forms a cycle. So this is called as a circular wait. Fine. So all these four conditions is a necessary condition if a deadlock happens, right? So what are the four conditions? Mutual exclusion. Next one is hold and wait. Third condition is no preemption. And fourth one is circular wait. So let's see now some special cases, right? So you should not say that if there is a cycle, then there will be a deadlock. No, it's a misconception that everyone has. So if it is a deadlock, then cycle will be there. Fine. If there is a cycle, you should not say it is a deadlock. So let's see some special cases. Case one is cycle with no deadlock, right? So here you can see, right, the cycle. This is a cycle, right? But we will not have any deadlock. We will check it, right? So here process 1 is blocked or not. Let's check. So process 1 is requesting for resource 1, but resource 1 is 2 instance of resource 1, right? Is occupied by process P2 and process P3. So process P1 is blocked now, waiting for resource 1. Let's check for process 2. Process 2 is not blocked, right? Because it requires resource R1 and it is granted. So not blocked. Process 2. Let's check for process 3. Process 3 is again blocked, right? Waiting for resource 2. Process 4 is not blocked. See here, process 2 and process 4 is not blocked, right? It can release the resources after process P2 and P4 finishes its job, and then P3 and P1 can execute. The system is in safe state, right? Right. So in this you have seen, right? So multiple instance resource. So you have to be very careful when it is a single instance resource and a multiple instance resource. Resource allocation graph with multiple instance. With multiple instance implies cycle need not imply deadlock. So this condition you should be clear upon. Okay, so a resource allocation graph, if a resource allocation graph with multiple instance, then cycle need not imply a deadlock. But if it is a deadlock, then there will be a cycle. Okay, so here there is a cycle but no deadlock. Okay, so let's see the next case. So cycle with deadlock, right? So here you see all have single instance, right? Here one instance, one instance, one instance. Fine, and there is a cycle. You see, cycle is formed, right? So this is a cycle with single instance. Fine. So if resource allocation graph with single instance implies cycle is necessary and sufficient for deadlock to occur. Fine. So if it is a single instance resource allocation graph, then cycle is a deadlock, right? If it is a multi-instance, then cycle need not imply a deadlock. So always cycle will not lead to a deadlock. Fine. But if it is a deadlock, definitely there is a cycle. Okay, but the converse is not true. In the next video, we will see the deadlock handling strategies.